Have you ever pondered over the practical application of the conservation of energy? Well, today we delve into an intriguing problem where this very principle is at play. Picture this: a spool with a light string wound around it, and attached to this string is a 3-kilogram bucket. The bucket falls 4 meters, starting from a state of rest, and the string unwinds from the spool without slipping. The question is, what is the angular speed of the spool after the bucket has fallen? To solve this, we apply the principle of conservation of energy, which states that the total energy in a closed system remains constant. In this case, the potential energy of the bucket at the start is converted into the kinetic energy of the bucket and the spool as the bucket falls. The potential energy of the bucket can be calculated using the equation for gravitational potential energy, which is the product of mass, gravity, and height. The kinetic energy of the spool can be represented as 1/2 times the moment of inertia times the angular speed squared. Setting these two equal to each other, we get the equation: 1/2 times the moment of inertia times the angular speed squared equals the mass of the bucket times gravity times the height the bucket falls. Solving for the angular speed, we get the square root of 2 times the mass of the bucket times gravity times the height the bucket falls divided by the moment of inertia of the spool. Substituting the given values into this equation, we find that the angular speed of the spool is approximately 10.9 radians per second after the 3-kilogram bucket has fallen 4 meters. So, through the principle of conservation of energy, we've managed to determine that the angular speed of the spool is approximately 10.9 radians per second after the bucket's fall. This shows how fundamental physics principles can be applied to solve real-world problems, making the world of physics not just fascinating, but also incredibly practical.